Hi everyone, and in this lecture we are going to see how we can use the ideas of Laplace transformations to turn a differential equation into an algebraic equation, and then using the inverse Laplace transformation how we can extract out the solution for that differential equation. So let's get started. I will be considering a very simple and a similar differential equation, namely the differential equation for the harmonic oscillator, and it will look something like this. Let's say d square x dt squared plus k by m x equals to 0. This is the differential equation we want to solve. And you have already seen how the derivatives transform under a Laplace transformation. So the idea here is to take Laplace transformations on both sides. So let's take the Laplace transformation of this whole equation. This d squared x dt squared. This is a constant, so it will just be outside the Laplace transformation. This k by m, Laplace transformation of x, right? And here you have 0. The Laplace transformation of 0 is just 0. So this is 0. Now, in your previous theory video, that means when you guys did Laplace transformations, you saw what is an expression for this. That means what happens when you take the Laplace transformation of a differential operator or a derivative. So this is a second order derivative, right? And the second order derivative will look something like this. This will be simply s square and x of s, where x of s is the Laplace transformation of x. Okay, so this is what I mean by x of s. Then there will be a minus, and it will contain some x0. By x0 I mean when x is at t equals to 0. That means this x0, this will mean x of 0, where this is actually the value of t. That means at t is equals to 0. So this will be just s x0, which is a number or a constant, whatever you want to call it. And finally you will have k of x of s. And there is a m underneath it, right? Now this is an algebraic equation because it should be s, not x. Now this is an algebraic equation. So our goal is to solve for x of s. We want to solve for x of s. So our Laplace transformation transformed our differential equation into an algebraic equation. And yes, this is the part that is coming from this guy, and this guy is over here. That is k by m, this guy. So I should have written it over here, so let me just write it down. L of x of t. So this part is coming from here, and this part, the part with k by m, is coming from here. And now we want to solve for x of s. If you solve for x of s, this is pretty easy because it's just a matter of pushing things on the right hand side and solving for x of s. This will just be something like this. X of s will be x0 times s divided by s square plus k by m whole square. Let's denote k by m as omega, and you can write it like s x0 s square plus omega square, right? this is the Laplace transformation of x of t. So x of s is the Laplace transformation of x of t. So how do you get back x of t? Because that's the thing we wanted to solve in this differential equation, right? We want to get what is x of t. And to do that, you need something called an inverse Laplace transformation. To do that, we need inverse Laplace transformations. And the inverse Laplace transformation is defined as, let's say this is the Laplace operator and you put an inverse on it to denote the operator itself, and if you apply it on x of s, it should give you back something called a x of t. And this is something you will see from the next videos, that how we can actually calculate the inverse Laplace transformations. For now, I'll just present you the result. That means oops, sorry, I made a mistake over here. It should be omega square. Yeah, it should be omega square, and there shouldn't be a square over here. Sorry about that. So as I was saying, that I'm just going to show you the result, but you will learn how to calculate the inverse Laplace transformation given any function, and you will learn it in the next videos. That means next 2 or 3 videos that will come. So our x of s was this guy. This is the function of interest, and if you do this inversion, you will get x of t as x0, cos omega t, which is a pretty familiar solution to each and every one of you. So this is a pretty simple example. And now let's say you have a differential equation, a second order equation. We won't go beyond second order, so something like this. Let's say t, x of t. Then you have this double prime, means is the second derivative. Then you have this bt, and let's say you have x prime of t, and finally you will have something called a c of t, which is equals to some f of t, right? This looks pretty complicated. Each and everything is a function of the independent variable t. Now you may ask this question, that can I apply Laplace transformation over here? The answer is yes. However, whether you can do the integrations or not, that's a matter of the boundary conditions, and at the same time what type of functions you are dealing with. To do it, you just put this Laplace operator over here. It's a linear operator, so it will go through these brackets and all these plus signs, and over here you do it, you find an expression for x of s, if it's possible, that means if it's integrable. Alright, and after that you need to solve for this x of s. When you are done finding x of s, all you need to do is you need to inverse the x of s. And before I finish, obviously I'm not going to talk about these kind of things, because most of the time the differential equations are pretty notorious to solve, and in some cases they're not even solvable analytically. So that's why I'm not going to talk about any differential equation that has this complicated form. Rather, I want to give a very schematic description of how this L inverse looks. So if you have your x of s, the x of t can be very schematically written as something like this. Sorry, it should be a plus sign. X of s, d s, something like this. However, the reason I'm putting this approximate thing is because the inverse Laplace transformation is actually defined via a contour integral that is called the Bromwich contour and the Bromwich integral. So if I write this whole thing down right now, it will actually look something like this. This x of t will be actually 1 upon 2 pi I, some contour that will look something like this. Let's say this is, oh sorry, this should be x. Alright. This is something like this, and these are the type of integrals you will see from the next videos. So this will be it for today, and thank you.